Hello, gang. Welcome to CSC 475, Artificial Intelligence. Today, what we're going to be doing is we are going to be talking about an hour and 50 minutes. No, today what we're going to be talking about is formal logic. Formal logic. So that's really the last part of the class. The last topic that we're going to talk about is formal logic and automated reasoning. And so it's going to start off being real similar to stuff you've already seen, and then it's going to get we're going to branch out into stuff that's not so similar. So what is formal logic? Well, clearly it's logic that dresses up in tuxedos and goes to fancy. No, obviously. So that's like two bad Mike jokes in a row, right? So I commiserate with all of you for having to live through those. Formal logic is just another name for symbolic logic. Basically what it is it's a way of representing information or knowledge or whatever word you want to use as symbols and symbol manipulation rules, okay? So we're going to have some symbols, and we humans are going to attach meaning to those symbols. The computer's not going to know those meanings, but we humans will attach meanings to those symbols, and then we'll have some rules that will allow us to manipulate those symbols. So really, all formal logic is a game that has symbol manipulation rules in that game, okay? But it's a game where humans have built the rules, so those rules reflect the way humans reason. Let me say that again. In formal logic, we're going to have some symbols. They're called propositional variables, okay? And we humans are going to map meaning to those symbols, but the computer system's not going to know what those meanings are. Together with those symbols, there will be rules, very formally defined syntactic rules that you can apply to these symbols that will allow you to derive other symbols, for example. And those rules that humans made up the rules of the game, those rules were selected in such a way that the game has meaning to humans, okay? So another way of saying this is it is a system that allows you to reason based on form, to reason based on syntax. And that's a really weird thing to think that we could even build such games, because syntax is the form that you write something. Like when you get a syntax error, when you are compiling a program, what that means is the form of your statement doesn't match anything that's recognized by that language. So you've said something that's not a valid way of saying it in the language, so you get a syntax error. Syntax is the rules for what is a legal statement and what is an illegal statement. So syntax in general has nothing to do with meaning. Meaning is semantics, okay? What something means is semantics. The form that you say it in or express it in is the syntax. Well, what's so weird about formal logic is it allows you to reason, okay, based solely on the syntax, on the form of something. And that seems really kind of bizarre to even say that. How can I reason about something when the system doesn't even know the things I'm reasoning about? It's just manipulating some symbols. Well, the answer is we've defined those rules for manipulating those symbols in such a way that they reflect human reasoning. Okay? So another way, a more informal way that you could think about formal logic and automated reasoning this is a Mike O'Neill definition, reasoning without understanding. That's what the system is doing. It is reasoning without understanding. And if that seems weird, think about a very primitive operation you can do on a computer. Adding two numbers together or multiplying two numbers together. The computer doesn't know what it's doing. The computer really doesn't even understand the abstract concept of a number. It's just through a series of and, or, and not gates, right? Moving and manipulating bits. But the result of that is, oh, it added these two numbers together, right? So we built the hardware so that it does what humans have defined addition to be. It doesn't mean the computer understands that it's adding. It's just, when you study digital logic and you study the CPU, it doesn't, it doesn't understand the concept of one quantity being greater than another. But you can do an if statement where you have a relational comparison that says if this is bigger than this, if A is greater than B, then do this other thing, right? So everything we do with computers pretty much is it's reasoning, it's doing these steps, but it doesn't know what it's doing. Okay, so there are lots of types of formal logics. We're going to start with the simplest, which is called propositional logic. Propositional logic. And I'm going to share my screen now. Propositional logic is just is the simplest kind of logic, and it's the one you're most familiar with. Oh, come on, be nice. Play with me. If you guys wonder what I'm doing when I'm taking this time and I bring up something like this, it's because there are other things on my screen other than the window that you see that I'm sharing. And so I have to get it so that I can get my scroll bar on top of things. So that's what I'm doing when I look like, why is he just staring at the screen with a puzzled look on his face? That's what I'm doing there. Okay, so you can see propositional logic. Propositional logic is a logic that is two-valued. So you can have variables like P and Q and R, and those variables can be mapped to concepts. Like we could, let's say, P mean it is raining, and Q mean I am wet, and R mean I am outside. The computer doesn't know those mappings to real world concepts. It just knows P, Q, and R. But when we think about problems, we assign concepts or ideas to those propositional variables. Propositional variables are binary. They can either be true or false. So if you look at the statements that I've attached to them, they're statements that can be either true or false. If I say, it is raining, well, I look outside right now and actually it is raining has a propositional value of false. Right now in Ruston, Louisiana, at this date and time, the value of that statement is false. Now, next week, or tonight or at some other time, the value of that statement might be true. But right now, the value of that statement is false. We can let Q be, I am wet. Well, that's also false right now because I'm dry, as you can see from the cam image. And R is, I am outside. Well, I don't know. If I were on the Elysium space station, would I be outside or inside? That's kind of a hard one. But no, I'm actually inside my home. As we know, that's a fake background. So I am outside is false. So all those happen to be false right now. But at various other times, those propositional values could be true. So again, these variables have propositions or statements associated with them, and those statements can be true or false. Now, the first thing that we have, another thing that we have in addition to propositional variables is we have logical operators. Now, what's a logical operator? Well, as I have it defined here, a logical operator is an operator that can be used to combine propositional variables together to form compound statements, right? And these compound statements can be either true or false. Now, there are three fundamental logical operators, and you know about these because you've had digital logic, right? You know about and, or, and not, and you know about these truth tables for and, or, and not that you've seen, again, ever since at least digital logic, or maybe even some other class before that. So how were these operators defined? Mike, can you give me a definition of and? Sure, I respond. I can give you a definition of and. The definition of and is given by that table that you see right here. This table is the definition of and. What do you mean, Mike, that table's the definition of and? Well, how do we read the table? Well, the table will have an input value for Q, an input value for P, an input value for P, and an input value for Q, and then it will have an output for P and Q. And is often written, computer science, as a little house rooftop, right? So it looks like an A, so that's how you can remember it's and. So P and Q. And this is the output, right? So when P is true and Q is true, then P and Q is true. When P is true and Q is false, P and Q is false. When P is false and Q is true, then P and Q is false. And when they're both false, then the output's false. Now, where did this table come from? Humans made it up, okay? Why is the operator called and? Well, humans, when they defined this logical operator that they're calling and, they built this table so that it captures the meaning of the word and. So if I were to say something like, it is a sunny day and Mike is inside. Well, I look outside, it is a sunny day, that's true. As I've already told you guys, Mike is inside, that's also true. So if I say it's a sunny day and Mike is inside, that's got to be true, okay? Because that's what and means. If it's not, if either of the propositions of the inputs are false or they're both false, then the output is false. If I say something like, Mike is big and strong, okay? Now, those of you who've only seen me over webcam may not know that, the meaning of that. But anybody who's seen me in person, if I were to say, Mike is big and strong, is that a true statement? No, of course not.
Yes.
Why? Well, Mike is big. Well, Mike is kind of big around his belly these days, but Mike is 5'2" tall, right? So that's not generally, that's not a big guy, right? No, I'm not strong. I'm sure if I got into a weightlifting contest with Arnold Schwarzenegger, even at his advanced age, he would, or Chuck Norris at his advanced age, either of those guys would easily win against me. So in that case, when I say, you know, Mike is big and strong, we're down here in this rule because Mike is neither big nor is Mike strong. So both of the statements are false. You know, but I could say something like, you know, Mike is short and exceedingly handsome. Okay. Well, maybe when I was 30, I wasn't so bad looking, but, you know, as I approach 60, you know, I think we would have to say false on the exceedingly handsome here, assuming you can see. So we're in this world here. But if I were to say, you know, Mike is short and exceedingly handsome, I think you would say, that's not true, Mike, because you win on the short, but you don't win on the exceedingly handsome. And you know, it could be in another world in which the P is false and the Q is true. But the point is for the conjunction of P and Q to be true, both P and Q have to be true. And that's the way we generally understand what the word and means in English. So we've defined the behavior of this operator to work like the word and in real life. And so we've called it and, the English word that expresses this idea. So we've taken one word of English and we've defined it in a very precise way by listing out all of the possibilities for the two things that the and connects. Both of those things must be true for and to be true. And I'm not going to belabor it, or maybe I will belabor it because it is very important. Or is the same sort of thing. We're going to call this operator or. We often express it in computer science as a V. That's because the Latin word is vel. So that's where the V comes from for or. And or works differently. Basically, or is if either or both of the inputs are true, then the output is true. The only time or is false is if they're both false. So if I were to say, what was I using here a moment ago? You know, Mike is either short or incredibly handsome. Mike is either short or incredibly handsome. Well, that's true because the short part is true, the incredibly handsome part is false, so the or of those two is true. Okay? Are there any questions about and or? No? Okay, not the same sort of thing. Not is just an inverter. It takes whatever the value of P is and flips it. So where and or are binary operators, they need two things. They need a P and a Q. Not just needs one thing. It's a unary operator. So it flips the meaning. If I say Mike is short, well, that's a true statement. If I say Mike is not short, well, that would then becomes a false statement, right? If I say, you know, Mike is handsome, that's not a false statement. If I say Mike is not handsome, that becomes a true statement. Boy, that's sad. Anyway, so it's very Freudian and psychological. You can tell what I'm thinking about from my examples that I come up with off the top of my head. He's obsessed with being short. Okay. But seriously, are there any questions about and or and not, and how these things work? Again, you've seen all of these things many, many times before, but they're the basis of everything that comes afterwards. And maybe you haven't quite thought of and or and not with English sentences attached to them, you know, rather than maybe bit values or something like that. Okay? So that's and or and not. Let's see. Okay. So the interesting thing about propositional logic is really all you need are propositional variables and or not. Anything that can be said in propositional logic can be said with the correct number of propositional variables and just and or not. But we don't stop there. We create additional operators, but these additional operators can be derived from and or not. So, the three main operators, the three basic operators, and or not, they just have truth tables that define them, okay? But any other operator that we talk about in implies, for example, A implies B. Or another way of saying that is if A, then B. That's implication is a derived operator. Derived operators can be described in two ways. You can describe them, you can define them with a truth table if you want to, or you can define them in terms of an expression that consists of and, or, and not. Maybe multiple ands, maybe multiple ors, but some expression involving and, or, and not. That's why they're called derived operators, because you can derive the operator from an application of and, or, not. Okay? So let's see. I think we covered everything in this little paragraph here about propositional logic. It's a game. The rules were defined to reflect the reasoning of man. And by the way, when you say man and capitalize the M, that means humanity. It's not male or female. It's all of us. But sometimes you'll hear people use a phrase like, from the mind of man or something like that. It just means people, humanity. So again, here's some, examples. It's a warm and sunny day. If P is warm and Q is sunny, then you could roughly translate it's a warm day into P and Q if you assigned P to warm and Q to sunny. Marcus would be happy if he's rich or famous. P is rich, Q is famous. P or Q saying rich or famous. Now you might say, well, what about this Marcus? He's not in here. That's true. We'll study a logic. We will study a logic either next lecture or the lecture after that allows us to do quantification, so you can talk about groups in that using two what are called quantifiers. You can talk about a particular individual, or you can talk about something that's true of all individuals of a particular group. But we're not there yet. But I just wanted to say, if I say P or Q, I'm really saying here rich or famous. This whole Marcus will be happy part of the sentence I'm dropping on the floor. It is not cloudy. P equals cloudy. So you could say not P, which means not cloudy. One other little thing here. Even at this very early date in what we're doing, you can see that when I said it's a warm and sunny day, and I said, well, I could approximate that by saying P is warm and Q is sunny, and so this says that it's warm and sunny. That's roughly it's a warm and sunny day, but I didn't capture the concept of day over here, right? Really, all this is saying is warm and sunny, and all this is saying is rich or famous, right? Formal logic is a game where the rules can allow you to reason without understanding, without the system understanding. So you can build systems that reason automatically. But one of the problems is that you may have heard garbage in, garbage out, right? That used to be said a long time ago. That was very common. I don't know if people ever say that anymore. But basically, there's no algorithm for taking a random statement in English and translating it into one and only one propositional logic formula, or even a predicate logic formula. Again, predicate logic comes. We'll cover that after we cover propositional logic. But the point that I'm trying to make here is that you're always going to lose shades of meaning when you go from English to logic. And so, you know, once things are in a propositional formalism, the rules of logic are built in such a way that it's not going to come to an illogical conclusion. But that doesn't mean that when you translate that conclusion back out to the real world that it makes sense, because the way you translated in the original statements, you may have lost some piece of the meaning that actually turns out to be really important that you didn't think was important when you did the translation. So I hope I'm making sense here. And I want you to keep that in mind, because a lot of times people they skip over that and they just go right to the formal reasoning, and they don't express this very, very, very important caveat, and just go, oh well, it logically follows, it must be true. Yeah, but what was that first step when you went from English to formal logic? Did you really do that properly, or not? And when you got a proposition, when you got a logical result, did you really map that back correctly to the real world? In fact, one of my favorite Doctor Who quotes. Yes, I'm a Doctor Who fan. One of my I haven't had a Doctor Who background, have I? I've got to make a note. I've got to have a TARDIS background on one of these lectures. I can't go through the whole quarter and not have a TARDIS background. That would be terrible. But one of my favorite quotes from the Second Doctor, way back in the black and white days, was his companion's name was Zoe, and she actually catches him in a lie, and the Doctor, to misdirect her, says, "Logic, my dear Zoe, is simply a way of being wrong with authority." Because she comes to him and she says, "Well, logically, Doctor, that can't be true." And he says, "Logic, my dear Zoe, is just a way of being wrong with authority." and there's a lot to be said about that, because sometimes people get, they get too hung up on a logical proof, not realizing that there actually could be problems with it. Okay, so let's look at some of these derived operators. The first derived operator is implication. P implies Q. It's usually written with this arrow like this. P implies Q. What does it mean? Well, it's an if statement. It's basically saying if P is true, then Q is true. So, and the P is called the premise and the Q is called the conclusion. The thing on the left-hand side of the arrow is the premise. The thing on the right-hand side of the arrow is the conclusion. Now, I'm saying P and Q. You could use any variables you wanted to for these. There's nothing magic about P and Q and R. They're just the first variables that I picked out of the air, and usually they're the P, Q, and R are usually the letters that people historically have used when they're defining these things. So our first question should be, well, okay, what does implies mean? Well, it means exactly what's in this table, because this table is the definition of implication in formal logic, okay? The next question ought to be, okay, Mike, this table defines this operator that you're calling implies, but as a human being who uses language and has for many decades, I have a understanding of what implication means. I understand what an if statement is. Do these rules that you have in this table really capture the English meaning of an if statement or implication? So let's think about that. And this is important, so we need to think through this one. Again, you've learned about and or and not in digital logic. You may not have done implies, right? So this starts to get to the newer stuff. So let's just look at an if statement. If you are in the pool, then you are wet. Okay, that's a very reasonable kind of thing to say. So I could say P is pool and Q is wet. I could have used a W for wet if I wanted to, but I used Q. So P implies Q. Pool implies wet. That's a very reasonable thing to say. So if I were to say if you're in the pool, then you're wet, okay? This if statement could either be true or false. It could be. I could be telling you something that's true, but I could be telling you something that is false. I might be lying to you, or I might be mistaken, okay? So this if statement could be either true or false. Now, I'm talking about the statement itself, the if statement itself. So if you're in the pool, then you are wet. If you really are in the pool and you really are wet, then this if statement should be true in that case. If I tell you, if you're in the pool, then you're wet, and you really are in the pool, right? That's what the T for under P means. If I tell you, if this statement is a true statement, okay, if you're in the pool, then you're wet, that's a true statement. And I also tell you that you're in the pool, right? Q better be true also, or something's wrong with this world. Does everybody agree with that? And when I say something's wrong with this world, I mean something would have been wrong with the way I defined implication if that hadn't been true. Now, when is this if statement not true? Well, if I'm in the pool and for some reason I'm not wet, then that if statement is false in that case. Each of these lines is a case, or sometimes it's referred to as a world. You know, when we talk about the many worlds hypothesis from quantum physics and different timelines and stuff like that, you can actually think of each line of this as a different reality, as a different timeline. That's really what it is. So in the timeline, in the reality where P and Q are both true, then that if statement in that world was true. But if I tell you that if you're in the pool, then you're wet, and you are in the pool, but you are not wet, then in that world, this if statement was false. It was incorrect. And you might say, but how can it be incorrect? If you're in the pool, then you're wet. That just makes common sense, Mike. I can't imagine a world in which, I can't imagine this world. And I'm like, well, think just a second. You can imagine this world. This world makes sense. Let's say that the pool is being cleaned, so it was drained. Okay, so the pool is being cleaned or repaired, and it's been drained. So I could be, maybe I'm working on repairing the pool. So I am in the pool could be true, right? I am wet could be false. Maybe I'm repairing it, and the pool's been drained. In that world, saying to someone, if you're in the pool, then you're wet, that's a false statement. Does that make sense? Is there any question from anyone about that line of the table? Okay. So people, students, human beings have no problem with lines 1 and lines 2 of this table. Okay. People start getting a strange look on their face sometimes for those 2 lines of the table. What are they saying? And why might the game of logic have been defined this way? Well, if I tell you, that, let's say the statement, if you're in the pool, then you're wet. Let's say that that's a true statement. Take it on faith that in the worlds that we're talking about, that's a true statement. We're not talking about worlds right now where the pool has been drained for repair. We're talking about worlds where it's really a true statement. If you're in the pool, then you're going to be wet. Okay? What if you're not in the pool? Okay? If you're not in the pool, how should we treat that if statement? If you're in the pool, then you're wet. If you're not in the pool. Or another way of saying it is, if I'm not in the pool, what does the if statement tell me about whether or not I'm wet? Well, it tells you nothing about, if you're not in the pool, you might say, well, if I'm not in the pool, I'm not wet. No, because in the world in which, if you're in the pool, then you're wet, the world in which the pool has water in it, so if you're in the pool, then you're wet, right? If I'm not in the pool, that doesn't mean that I'm dry. I might be standing outside and it might be raining. That could also be true in the world where the statement, if you're in the pool, then you're wet, is true, right? Or maybe I'm taking a shower, right? And I'm wet. Or maybe I'm super lucky and I'm gone on a trip to Australia and I'm, diving along the Great Barrier Reef and I'm wet. There are many. There are an uncountable, an infinite number of ways that you can be wet in which you're not in the pool. So when someone uses an if statement and they say if A then B or if P then Q, that's listing one way that Q could be true. It's not saying this is the only way you could be wet. You could be wet in lots of ways, but here's one way. If you're in the pool, then you're definitely wet. In the worlds in which this statement is true, okay, and you're not in the pool, the statement says nothing about your wetness or not wetness. You can't conclude anything about wetness in the worlds where you're not in the pool when the if statement is true. And that's what these last two lines of the table is trying to say, okay, or actually is saying. It's not trying, it is saying it. So in these, notice P, that is, I'm in the pool, is false, okay? So I'm not in the pool in either of these cases. The if statement is true, and I could either be wet or dry. We have to give a value of T to this if statement because we're basically recognizing that when the premise is false, the conclusion can be either true or false. Neither of these cases would make the if statement a lie. In neither of these cases would the if statement be shown to be a lie. Having the statement, if you're in the pool, then you're wet, be true is consistent if you're not in the pool with either you being wet or not wet. And that is why these last two lines exist. The if statement is true, but it's said to be vacuously true. It doesn't tell you anything. The if statement's true, but you can't use it to tell you anything about your wetness or not wetness because you're not in the pool. So when you're not in the pool, the fact that the if statement is true, the statement doesn't tell you anything about your wetness. Does that make sense? Does that make sense? I'll go to full screen video on me. If there's any questions, ask them. Okay? Again, it couldn't be any other way. If you would screw things, so you might say, well, I guess I see what you're saying, Mike, but I'm a little uncomfortable with calling the if statement true in the case that I can't use it to conclude anything. And I might say, okay, well, are you going to put a false on that if statement in that case? Well, that would clearly be wrong because you're saying, well, I know this statement to be a lie, or I know this statement to be incorrect if you put a false here. But you don't know that. You didn't. If I'm not in the pool, and you either being wet or not wet, either one of those is consistent with the statement being true. It doesn't make it a lie. We put an F here on the value of P implies Q because the statement is false in the case where you're in the pool, I'm in the pool, and I'm not wet. Then telling someone, if you're in the pool, then you're wet, and they're in the pool, but they're not wet, well, then that if statement wasn't true. You were either incorrect or you lied to them. Maybe you knew the pool was drained for repair, so you were lying, or maybe you didn't know that. Maybe you really thought there was water in the pool. And maybe it's an above ground pool and you thought there was water in it, but there was a hole in the pool and all the water drained out. I mean, so if in that case, if you tell someone, well, if you're in the pool, then you're wet, not in that world. You can, if there's no water in the pool, you can sit in there all day long and still be dry. Okay, that's an example of implication, and I've tried to explain here. What did I do here? I tried to explain that the rules that humans came up with to define what implication means in formal logic make sense to human beings. We human beings could have defined any truth table, but this is the truth table that really reflects the meaning of an if statement being true or false. Okay? All right. Now, okay. All right. Next thing we want to talk about. Now, implication is not the only derived operator that you can have. There can be other derived operators, but there can be something like an if and only if, or an equivalence can be defined, where you're basically saying the truth value of both of these things is the same. So that can be defined too. But and, or, and not and implication are pretty much the most important, the granddaddy kind of operators in propositional logic, and or not are basic operators that are defined just by truth tables. Implication is a derived operator, and I still haven't proven that, but we're about to. So I'm going to move the conversation a little bit, and we'll start talking about rules for symbol manipulation. So one of the things that we want to do, the thing that we really want to do most often, is we want to substitute one expression for another expression. Why we would want to do that? One reason why we might want to do that is to simplify an expression. Another reason why we want to be able to do substitutions is, we're not going to get to it today, but next lecture I'm going to show you a way of reasoning with a number of rules, and then we'll simplify it to just one rule, which allows computers, which allow you to write pretty simple computer programs that can do automated reasoning. So we'll have substitution rules. The other kind of rules that we'll have is we'll have inference rules. So substitution rules let you swap one group of symbols for another group of symbols. And why do we do that? Because we want to get our symbols in a particular form, for example, or because we want to simplify an expression, just like you might want to simplify a mathematical expression. Inference rules are another thing that we're going to look at, and inference rules are rules that you normally only use when you know all of your premises are true and you want to find other things that are also true. Let me say that again. So far, when we've talked about and, or, and not, and we've talked about implication, we've talked about all possible worlds. If you've got 2 binary variables, there are only 4 possible worlds. If you had 3 binary variables, you could have 8 possible worlds. If you had 4 variables, it could be 16, and so on and so forth. It's powers of 2. But we've been talking about all possible worlds. When we start using inference rules, as you'll see here in a little while, we're generally interested only in the worlds in which the premises are true, right? So the worlds in which the variables are true, and what we're trying to do is see if we can find other true things that are implied by what we already know. So we use inference rules to find new knowledge that is logically implied by existing knowledge. Okay? We'll get to it, but I wanted to explain that when we get to inferences, things are going to change a little bit because we're not going to be talking about all worlds. We're going to be talking about we'll concentrate on just the worlds in which things are true. Okay, but let's look at substitution rules first. And the first substitution is very simple. Double negation cancels itself out, right? Now, we learn in English way back in the day not to use 2 nots in a sentence. It's not good to use, to use, it's not good to use to use 2 knots in a sentence. And why? Well, because logically, 2 knots cancel each other out because a knot flips the meaning of a variable, and if you flip it twice, you're back to where you started. We refer to that in English as double negation, right? Double negation. So, you're strongly encouraged not to use double negation in English. But like everything in English, because it's a human language, it's a natural language, there are exceptions. For example, most people would consider it perfectly grammatically, i.e. syntactically, correct to say something like, I suppose it's not impossible that blah, blah, blah. I suppose it's not impossible that Biden could win the election, right? Or I suppose it's not impossible that Trump could win the election, which equal opportunity, whichever side you're on there, right? But a phrase like, it's not impossible, well, what does it mean when I say it's not impossible? Well, it's possible, right? So that is an example of a double negation that is allowed in English because the word impossible, what does it mean? It means not possible. So when I say it's not impossible, I'm saying it's not possible. And those nots cancel each other out. Now, remember again, I said that you lose shades of meaning when you go from English to logic. Do we lose a shade of meaning when I go, I suppose it's not impossible that Biden win the election? What am I really saying there? Human to human, what am I saying there? Am I just saying, it's possible that Biden wins the election? I've forgotten the reason, Biden or Trump. Am I saying that it's possible? Well, let's see. As Jonathan wrote there, the connotation is that it's unlikely or very unlikely. So when a human says, "Well, I suppose it's not impossible," they're saying, "Yeah, it's possible, but the probability is really low." And you lose all of that when you go, "Oh, I'm going to translate that to not P," right? So you can lose shades of meaning. So again, when you take English and you move it to propositional logic or any form of logic, you can often lose meaning. But if we look at the truth table for how not P works, you can start with P. P can be either true or false. You can not it, so the true becomes false and the false becomes true. And then you can take this column and you can apply a not to it, which is what I do here. So that F switches to T and this T switches to F. And if you look, P is true false and not P is true false. So double negation cancels. P is equivalent to not P. So if I had a logical expression and I had two nots in there, I could simplify it by just getting rid of those knots, just replacing not P with just the variable P. So that's an example of a substitution rule that can be used to simplify a logical expression. Make sense? Everyone nods their head. You know what I think I'm going to do at some point? I might do this if I teach online again next quarter. Actually, I might start doing this quarter. Is have everyone have to run their cam, right? Because sometimes I need to see faces because I'm like I say things and I get no visual feedback. And also too, it might make it a little harder for people to order drive-through during my lecture. So I know I'm going off on a tangent here, but I really am worried about you guys. We lost 25% of the class due to the second programming assignment, the first programming assignment combined with the exam, and that exam was no harder than any exam I've ever given in this class over the last 3 or 4 years. And I really, if anything, I took material out of the lectures rather than added material. And yet the grades were still lower than average. And on the programming assignment, I literally had, out of the 40 people in the class, I had 10 who couldn't do it, who just either didn't try. Well, here's another little secret for all of you who are still here. So far, I'm still working with one student, but everybody who tried has made and presented, worked on the program and presented it to me. Everybody's gotten at least a 50. Because what I'm doing is I'm working with anyone who wasn't able to get the program working completely to at least make sure they get a 50 on it. But even doing that, we lost 25% of the class. And why did we lose it? I think we lost it because when I teach in person, I don't let you use your phones and I don't let you use your computers. I make you pay attention and take notes the old-fashioned way by writing stuff down. And I know students hate that, but it forces you to concentrate on the lecture and the material. And, when I'm sitting here at my kitchen table and I don't see you, it increases the temptation for you to keep me in the background, while you're, sending messages on Twitter or whatever the current hot thing is. And I can't stop you. I can't kick you out of class for that. And the result is that people aren't paying as close attention to the material. And if you have me on in the background, he's going to drone on for 2 hours. I'll put him on in the background. That doesn't cut it with material that is, intellectually engaging. You have to engage. Anyway, enough of that that side lecture. It's just that if somebody, how about this to put a positive spin on it? If somebody has suggestions, I would appreciate email or meeting with me during my office hours over Zoom to give me some suggestions. Like I said, one I'm thinking about is just next quarter, insist that people run the camp during the lecture, and that'll help, I think, a little bit maybe to help encourage people to pay attention to the work. Okay, enough ranting. So double negation gets rid of itself. So if you've got two knots next to each other, you can just delete them and use the variable itself. Now here's another substitution rule, and you can argue whether or not you think that it simplifies an expression. You might say, well, Mike, it looks like it makes it more complicated. P implies Q is equivalent to not P or Q. Now you might say in a couple of ways, that don't make no sense to me. Okay. Because I don't think of if, if P then Q, I don't think that not P or Q, I don't see how that's saying the same thing at all, Mike. Well, let's first prove that P implies Q really is equivalent to the expression not P or Q. So how can we prove that? Well, we can prove it by looking at the truth table for P implies Q. We've already seen this. I presented it just a few minutes ago. And then you can say, okay, well, let me build a truth table for not P or Q and see what it comes up with. So I need P and I need Q. So true, 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 false, false, true, false, false. And then I'm going to take the P and I'm going to not it. So not P. So that was true, true, false, false. So it becomes false, false, true, true. And then I'm going to take the not P and apply OR with the Q using the way the OR operator works. So I wrote it as not P or Q. You could write it just as easily as Q or not P. They would mean exactly the same thing. So true or false, using the definition of OR, is true. False or false, using the definition of OR, is false. True or true is true. And false or true is true. So the truth value for not P or Q is true, false, true, true. Compare that to the truth table for P implies Q. True, false, true, true. That means they have exactly the same truth table. They have exactly the same definition. Okay? So P implies Q absolutely is equal in the game of logic to not P or Q. Do you see that first? Okay, that by the definition of how not works and the definition of how or works, that not P or Q matches the definition of P implies Q. And that's actually really important because I said that P implies Q is a derived operator. And I said it could be derived from ands, ors, and nots. Well, we didn't need the and, but here is how you derive it from not and from or. Okay, so let's see. Does it make any sense in English, or can we think our way through it to see whether or not it might make some sense? Well, how about if I say something like, on sunny days, weddings are held in the garden. On sunny days, weddings are held in the garden. So P is sunny day and Q is garden wedding. On sunny days, weddings are held in the garden. Now, the word if doesn't appear in that statement, but you can see that on sunny days, weddings are held in the garden roughly translates in English into, if it's a sunny day, then the wedding's going to be in the garden. Okay? So that teaches you very importantly that you can take an English statement that doesn't have the word if in it, and sometimes it really is an if statement. It's just said in English in a different form. So on sunny days, weddings are held in the garden. Can we think of a way that we could say that with not and or? So it would come out as roughly like this. Either it's not a sunny day, or weddings will be held in the garden. Now think about that carefully. On sunny days, weddings are held in the garden. So what does that mean? It means, well, if it's a sunny day, then the wedding's going to be held in the garden. If it's not a sunny day, the wedding's not going to be held in the garden. So saying either it's not a sunny day or weddings will be held in the garden, you're really saying exactly the same thing. Okay? So we don't normally think of an if statement. In English, we almost never take an if statement, right, and translate it into, not P or Q. But you can do it, and it does mean the same thing. If you're swimming in the pool, then you are wet. If you're swimming in the pool, then you're wet. Either I'm not swimming in the pool or I'm wet. If I'm swimming in the pool, then I'm wet. Either I'm not swimming in the pool or I'm wet. Because if I am swimming in the pool, I'm wet. Do you see that even in English, it feels a little tortured, but even in English, you're saying the same thing. Okay? And let's see, the third one here. Well, not P and Q as a quantity is equivalent to not P or not Q. If I were to say something like, Conan the Barbarian is not both strong and smart. Conan the Barbarian is not both strong and smart. Strong and smart. Not both strong and smart. Well, that means that either Conan the Barbarian is not strong or Conan the Barbarian is not smart. And if you've ever read the books, well, Conan the Barbarian is quite strong. He's not really a mental giant. So he's kind of your strong dumb type. So this one is easier. 3 is easier to understand than 2, because we do this in English a lot of times. You'll say not both A and B, and what you mean is either not A or not B. So a lot of times we'll say not both A and B, and what we really mean is not A or not B. So that one's, Conan's not both strong and smart. Yes, he is strong, but no, he's not smart. So one or the other. Okay. Okay. Does that make sense? Yes, no, maybe. Let's see. You guys have been chatting over here. Did we ever get those wings? You'd see my awful posture. I'm sitting like the letter M. Well, you get to see my awful posture. I slump my shoulders. Oh, that's actually kind of cute. Okay. It doesn't not make sense. That is fantastic. Thank you, Haley. Thank you. That is great. Okay. All right. Okay, so next up, what do we want to do? Well, I've talked through this whole next page of notes, and we're down to here. So remember, before I jump into that, remember what I said we were going to do. I said we were going to talk about substitution rules, which are ways of replacing one group of statements for another, or one group of symbols for another, and I showed you 3 substitution rules. I showed you double negation. I showed you that implication is equal to, equivalent to not P or Q, and I showed you that not over a quantity that's ANDed becomes not the first item or not the second item. So we've gone through substitution rules. Now what we want to do is go through inference rules. Inference rules allow you to, if you assume that all of your statements up to now are true, it allows you to infer additional true statements. So that's how we're going to use inference rules. Okay, so what are these inference rules of which you speak, Mike? Okay, there are 3 basic inference rules. And I use the old-fashioned Latin names for them. Fewer and fewer profs are doing that these days, but hey, I like the old-fashioned Latin names. So you have modus ponens, modus tollens, and then chaining of implication. These are 3 rules of inference that you can use to ferret out new things that are true based on some things that you know being true. So let's look at modus ponens. Modus ponens is probably the simplest thing. Even a baby can do it. And it's kind of one of the first things we learn to do when we reason, okay? Modus ponens is saying that if I tell you and you believe if P implies Q, that if statement is true, and you believe that P is true, you can conclude that Q is true. So going back to our pool and swimming example, if you're in the pool, then you're wet. That is an if statement. Let's say that if statement is true. If it's also true that you are in the pool, then you can conclude categorically Q, that you are wet. So given an if statement that's true, P implies Q, and given P is true, you can conclude a new thing. You can conclude that Q is true. Okay? You might say, but wasn't Q true, Mike, when you told me the if statement? No, we were talking about the if statement itself being true. Saying that the statement, if I'm in the pool, then I'm wet, that if statement is true about this world. And saying that in the world I'm in, I am in the pool. Well, then you can conclude in this world that we are in that you are wet. Okay? Now, what does all of this look like? Well, I should be able to generate a truth table for this thing. And when I do, I find something kind of interesting. I find that the statement is true in every possible world. Modus ponens is a tautology. A tautology is something that is true in all possible worlds. So that's basically saying that no matter what the truth values for P and Q are, that this statement is always true, okay? And 2 things. One, we can prove that this little complicated statement here is always true by tracing through and generating the truth table that'll always have T's in it. But the way we use it is to generate new knowledge. We use it only in the world normally where the P implies Q is true and the P is true. So the world that we're interested in generally is the world in which the if statement is true, so this is true, and the P is true. Well, in that world, Q must also be true. The expression is true no matter what the underlying values of P and Q are, but you come up with cases that aren't really useful. Like, let's go through. So give me P and Q. P implies Q. We've got a definition for that, so that comes out as true, false, true, true. We've already done that. So given this row that's got P implies Q, I could use and P, this column here, right? I could take this column here and it with this column here. True and true is true. True and false is false. False and true is false. False and true is false. And so I see that in this case, P implies Q being true and P being true is only true in this first case, where, of course, P implies Q is true and P is true. But also, look, what we're saying here is implies Q. So take this column right here, right, and then it with the, imply it with the Q column, okay, using the implications operator that we've defined, right? Well, true implies true is true. False, when this is false, we remember that the statement, the implication is always true if the premise is false, because it's vacuously true in these three cases here. It's vacuously true. It's true, but it doesn't tell us anything, right? So P implies Q and P implies Q is a tautology. It's technically true in all worlds, but we use inference rules generally only in those worlds where the statements that we have are both true. So the if statement is true and the premise is true, then the conclusion must be true. That's how you use modus ponens. So let me give an example. If Josh is at home, then he's playing Halo. Josh is at home. Assume both of those statements are true. So suppose I'm correct and I'm not lying to you. I'm telling you the truth if I say, if Josh is at home and he's playing Halo. Now, in the real world, people do other things. They sleep at home and they do. But in our world, if I say, if Josh is at home, he's playing Halo. Always. Whenever Josh is at home, he's playing Halo. And I tell you, Josh is at home. What can you conclude in that world? You can conclude that Josh is playing Halo, right? The other worlds here deal with situations where I'm wrong in some way. So like this line here, the second line, the if statement's false. So when I say if Josh is at home and he's playing Halo, Josh is at home, but he's not playing Halo, right? Well, how can that be? That if I tell you if Josh is at home and he's playing Halo, and Josh is at home and Josh isn't playing Halo, how could that be true? Well, it's true because that if statement was wrong. Maybe I was speaking metaphorically. When Josh is at home, he's playing Halo. Maybe I meant when Josh is at home, he's usually playing Halo if he's awake. But I didn't say that. I shortened it and said if Josh is at home, he's playing Halo. Well, clearly, Josh might be at home and he might be sleeping. So in that world, that if statement was not true. Okay? So you can't conclude anything. If the if statement's false, you can't conclude anything about Josh playing Halo or whatever. This third line here is the if statement is true in this world. If Josh is at home, then he is playing Halo. That's true. But, hey, Josh is not at home right now. So in that case, right, Josh might be playing Halo, or he might not be playing Halo. The if statement is true in both of these cases, but Josh is not home, so Josh might be playing Halo or he might not be. Maybe Josh plays Halo at places other than his house. It didn't say the only place Josh plays Halo is at home. It said, hey, if he's home, he's playing Halo. But maybe Josh also likes to play Halo at his buddy Chris's house, right? So if the if statement is true, but the premise is false, I cannot conclude anything about Q, okay? And we kind of talked through this already, but what I'm showing you here is that the rule of implication, modus ponens, is a tautology. That this implication is always true. It's just that it's only useful when the if statement is true and the premise of that if statement is true. Then you can conclude that the conclusion of that if statement is true. The useful world is this first world for modus ponens. Does that make sense? Questions, comments, vegetables you would like to throw at the instructor? You will have a hard time doing that over the internet. So we talked through all of that. Let me look at modus tollens, is the radishes. Good, okay. Modus tollens. Modus tollens is like modus ponens, only it reasons backwards. If I have a if statement that's true, and I know that the conclusion is false, I can conclude that the premise must also be false. It sounds like a lot of words, okay? But let's think our way through it. We'll use the same example. If Josh is at home, then he's playing Halo. Okay? If Josh is at home, then he's playing Halo. And we're meaning this to say that anytime Josh is at home, he's playing Halo. He's never sleeping, he's never in the shower, he's never cooking dinner. If he's at home, he's playing Halo. Okay? Because that's what it says. But let's say I know that this statement is true, that when Josh is at home, he's playing Halo. But let's say I also know that Josh is not playing Halo right now. How could both of these sentences be true? The sentence that says, if Josh is at home and he's playing Halo, that's true, and the sentence where I say Josh is not playing Halo. The only way those two could be consistent is for what? He's not home. Exactly. If the sentence, if Josh is at home, he's playing Halo, and if the sentence Josh is at home, if both of those things are true, then Josh is not at home. If Josh is at home, then he's playing Halo. If that if statement is true, and it's also true that Josh is not playing Halo, let me say it right, then the only way those two statements can be true is for Josh to not be at home. He isn't at home. Now, what does that look like as a truth table? Well, it looks like this. You will note that this modus tollens is a tautology. It is true in all possible worlds, but it's really only useful in the world where the if statement is true, right, and Q is false, because we're talking about not Q needing to be true here. So if not Q is true, then Q is false. So in the world where the if statement is true and playing Halo is false, then in that world, being at home is also false. So the useful line of the truth table is line 4 in this case. This is the world. This is the world in which we, this is the world in which we use modus tollens. Okay. But let's make sure we understand the other lines of the table. So what about line 2 of the table? What is it saying? Well, it's saying the if statement's false. Well, we already know if the if statement is false, you can't conclude, well, the if statement's false. So since the if statement is false, Josh could be at home and not playing Halo. Because I lied to you, or I didn't lie to you. I did. I lied to you. I told you something that's wrong because I didn't think about the fact that sometimes Josh is sleeping and sometimes Josh is making dinner and things like this. So this is the world that applies to those cases that I forgot about when I told you that if Josh is at home, he's playing Halo, and Josh is not playing Halo. He's not playing Halo while he is at home because he's snoring in bed. Okay? So this is a world, right? It's not a world where you can conclude anything about Josh being at home or not, right? Because the if statement itself was false. There are two other lines of this table, line 1 and line 3, and these lines point out a logical fallacy that humans often make. Okay, let's step back from Josh and Halo for a moment and go back to our pool example. If you're in the pool, then you're wet. Let's say that if statement is true, and let's say that I am not wet. So in that case, what must be true? If you're in the pool, then you're wet. I'm going to say that that's true in this world. And I'm also going to say that I'm not wet is true in this world. So what does that mean in this particular world? If I'm in the pool, then I'm wet. That's true. I'm not wet. So what does that mean? It means I'm not in the pool. Okay? A lot of times humans goof up and they say something like, if I'm in the pool, then I'm wet. Okay? And they say something like, I'm not in the pool. And they want to, and we naturally want to conclude, well, then I'm not wet. But that's not modus tollens. That's not a rule of logic, because like I said before, if you're not in the pool, it doesn't mean you're dry. It doesn't mean that you're not wet, because there are other ways you can be wet, and the if statement is just giving you one of those ways, one of those worlds. And so that's what line 1 and line 3 in modus tollens are trying to tell you. Stop editing your notes, Mike. The if statement is true in both of these worlds, right? So if you're swimming, then you're wet is true in both world 1 and world 3. But but what we wanted to say was, okay, what happens when the if statement is true, but the premise is false? Well, in that case, if the if statement is true, but the premise is false, it can go either way, because it could be either true or false. So you have to be careful that you don't make the mistake where you forget about the possibility of line 3 here, where the if statement is true, but the premise is false, because in that case, Q could be either true or false. And humans frequently forget that. They think, oh, if I say, if I'm in the pool, then I'm wet, and I say, but I'm not in the pool, well, then that means I'm not wet, which would be, here's the non-rule. I will edit here. This is not a rule. And I will put it in red because this, and try to do a truth table for this thing here and see. And you'll see that you don't get a tautology. This is not a correct rule of reasoning, right? And the reason why it's not a correct rule of reasoning is that when the premise is false, the if statement says nothing about Q. It may be true, it may be false. So there are worlds in which this thing is not true. Okay? Okay. Fake news, exactly. But it's the kind of logical problem that you see people make all the time when they're arguing something. You'll see them do it all the time, and knowing about logic, you can go, no, that's not. You're not actually reaching a valid conclusion there. You forgot about this case, right? An if statement isn't saying the only way something can be true. An if statement is saying a way this can be true is thus and such, and people get those confused, and it happens a lot of times in conversations if you notice. Okay, but we're not going to make that mistake because we've learned about what modus tollens is. If you've got an if statement that's true and the conclusion of that if statement happens to be false, then you know that the premise has to be false. That is a valid rule. That is using modus tollens. But that's different from the if statement being true, the premise being false. In that case, you can't conclude anything. And humans get those confused. But when you think about it carefully, you see one really is a rational reasoning rule. The other is a nonsense that people get confused over. And it all boils down to the fact that if statements aren't saying the only way something can be true. If you want to say the only way something can be true, you say if and only if. And you see that in math sometimes. And in the first time you see if and only if, you're saying, why are they double saying that? Well, it's because they're trying to say, if this is true and only if this is true, then this other thing has to be true. When in English, if we say if this is true, then this other thing is true, we're leaving open the possibility of other cases. Okay. What about chaining of implication? This is another thing that even the babiest of babies can understand. So modus ponens and chaining of implication, humans don't make mistakes on those, and they're obvious to children. Modus tollens you have to think about, but once you think about it, you go, yeah, that makes sense. I say it does make sense. It is right. And yes, I can see that we do sometimes goof up trying to apply a non-rule that kind of seems like modus tollens. But the first one, modus ponens and chaining of implication, these are both obvious. If I tell you if P then Q is true, and I tell you that if Q then R is true, then you can conclude a new rule, P implies R is true. Oh, what is he saying here, Mike? You got all this crap. But it's easy. If I say something like, if you're human, then you're a mammal. And if you're a mammal, then you're an animal. So what do you know has to be true there? If I say, if you're a human, then you're a mammal. If you're a mammal, then you're an animal. You automatically know, oh, then if I'm human, I'm an animal. Right? That's all this is saying. If I'm human, I'm a mammal. If I'm a mammal, I'm an animal. So therefore, if I'm a human, I'm an animal. If me human, then me animal. That sounds like George of the Jungle to me. Okay. So that is chaining of implication. Again, if you work through the whole truth table, which you should do, you will see that this rule is true in all worlds. That's great. What world do we use it in? We use it in the world where both of the if statements are true, right? If that's the case, then the concluding if statement will also be true. Okay. All right. So now that we've explained these inference rules, I went through all these notes already. We're down to here. I'm now going to change rule. I'm going to change what we're doing, and we're only going to be talking about the worlds in which the statements that I give you are true. So no longer are we going to be talking about all worlds. We're going to be using inference rules to discover new knowledge, but we're going to be using those inference rules to discover new knowledge in a world where I'm giving you some statements and we are accepting that those statements are true. Now, if I screwed up in some way and give you a statement that isn't actually true, right, then the conclusions you come up with could be totally inapplicable to the real world. But given a set of statements, if these statements are all true, we can use inference rules. We just looked at modus ponens, modus tollens, chaining of implication. We can use those rules to discover new knowledge, knowledge that is implied in the stuff that we've already, it may not be obvious, but it's implied in the knowledge you already have. So we will be able to reason about a situation to come up with logically true statements. So number one, if you go swimming, you'll get wet. I'm guaranteeing you that if statement is true. We're leaving out, well, if you're swimming, I don't say swimming pool. If you're swimming, you're going to be wet, all right? I'm leaving out worlds in which you're wearing a diving bell. Well, I don't know. A scuba gear. Does scuba gear keep you dry? I don't know. It's called a wetsuit. I don't know. But we're leaving out any world in which you could be swimming yet not be wet. So if you go swimming, then you'll get wet. If it's raining and you're outside, then you'll get wet. We are accepting this as a true statement in the world we want to discuss. We are leaving out worlds in which you're holding an umbrella over your head. Okay? But in the worlds we want to discuss, if it's raining and you're outside, then you'll get wet. We also have a statement, if it's warm and there's no rain, then it is a pleasant day. And that's a statement that's very true as I look out my back window. I'm also telling you that you are not wet. I'm telling you that you are outside, and I'm telling you it's a warm day. So the first thing we want to do is, if we want to reason about these statements, is we have to translate them into propositional logic. And I'm going to drop using P's and Q's and things like that now and use variable names that are meaningful to humans. Why am I doing that? For the same reason we use variable names in programs when we write computer programs, where the variable names are meaningful to humans. You don't have to use meaningful variable names, but they sure help the human keep track of what's going on. So I'm going to translate one into swimming implies wet. If you go swimming, then you'll get wet. Swimming implies wet. If it's raining and you're outside, then you'll get wet. So rain and outside as a quantity, both of those things imply wet. If it's warm and there's no rain, then it's a pleasant day. So I encoded that as warm and not rain as a quantity. Both of those things imply pleasant. Could have said pleasant day if I wanted to. You are not wet, so that's not symbol wet. You are outside, so that's outside. And it's a warm day, so I said warm. So now we've translated the English into propositional logic using meaningful variable names. So what can we do with this? Well, assuming all of those statements are true. So we're assuming that. We're only in the world, in the line of the truth table, where all of those statements are true. Okay? So I can conclude that I'm not swimming. How can I conclude that I'm not swimming? Well, you can apply modus tollens using Rule 1 and Rule 4. Swimming implies wet. That's given as true. Not wet is given as true. How can those two things be consistent? Modus tollens tells us they can only be consistent when not swimming is true. Okay? Does everybody see number 7? How I proved that I'm not swimming. And does that make sense? Well, of course it makes sense, because I told you if you go swimming then you'll get wet, and later on I told you you're not wet, so you're not swimming. It's just the rules of propositional logic work. It is reasoning, and the conclusions that it's coming up with are conclusions that a human would say are logically valid. Okay, how about trying to prove that it's not raining? So, does it make sense that it's not raining? Well, we know it's a warm day, and if there's no rain, then it's a pleasant day. But we don't have anything that says that it's not raining, do we? Okay, so how can we solve this? Well, if you go and look at applying modus tollens to Rule 2 and Rule 4, modus tollens to Rule 2 and Rule 4, Rule 2 says if it's raining and you're outside, then you're wet. But Rule 4 says is I'm not wet. So I know from modus tollens that it's not both raining and I'm outside. So I know that not, open parentheses, rain and outside, close parentheses, must be true. I know that from modus tollens. Okay, cool. I can also simplify this statement to say that if I know that not both rain and outside, that translates into either not rain or not outside. Okay, so I've got not rain or not outside. Now, statement 5 says that I'm outside. So if either it's not raining or I'm not outside, and I know that I'm outside, well, what do you naturally conclude? Well, you naturally conclude that it's not raining, right? Now, we haven't actually proven this. We haven't actually generated an inference rule that says that you can conclude not rain from this thing. So what I want to do is I want to come up with a new rule that says this. If it's not raining or I'm not outside and I'm not outside, I can conclude that it's not raining. If I tell you either it's not raining or you're not outside and you tell me that you are outside, then the only way that this statement, this or could be true and this outside could be true is for it to not be raining. We can prove that. I can build you a little, I can take this thing and I can say, well, build me the truth table for this, buddy. And if you build yourself the truth table for it, you see it's a tautology. And when something is a tautology, it is a inference rule, because it's true in all worlds. And so this lets us say that not P or not Q, that's true, and Q being true. So I guess we're looking at what, line 3 here, right? That tells us that the premise must be false. So that works. So that gave us that it's not raining. Okay. Finally, can we conclude that it's pleasant? Well, we knew it's warm, and we've proven that it's not raining, right? We've already proven that, so that added in line 8. And statement 3 says, if it's warm and it's not raining, then it's pleasant. Warm was given. We've proved no rain. So because both of those things are true, making this and premise true, it's got to be true that it's pleasant. So we concluded 3 new pieces of information. If you translate them back into English, we can add this to what we know. You're not swimming, it's not raining, and it's a pleasant day. And we did that. We could do that automatically, just using these syntax rules that we've come up with by a computer program that can reach these conclusions. You can feed it a story like this. Now, you really kind of need to feed it a story already in this form. A lot of work went in over the years trying to take English and convert it to logic. But if you give me the story in propositional logic, a simple program could conclude these 3 things, which translated back to English roughly say, I'm not swimming, it's not raining, and it's a pleasant day. Now, that is pretty effing amazing, and I'll use effing because this is being recorded. Okay. We have reasoned about, a pleasant day outside, and have come up with 3 additional pieces of information that are all logically consistent. No human would argue with you that it isn't true that, given what I gave you before, that you're not swimming, it's not raining, and it's a pleasant day. But we can do this simply by a system that is just using symbol manipulation, syntactic symbol manipulation. And so you can see, hopefully, why in the early days of AI, and even some people to this day, got so excited about this, because I can take a machine and I can get it to reason about the world and come up with conclusions that are true, and it's doing this mathematically. It's thinking, right? I mean, it's reasoning. Let's not say thinking. It's reasoning, and that's pretty amazing that you've mechanized a small part of the process of thinking. Some people might say it's a large part of the process of thinking. And so this is why people, like I talked to you about Doug Lenat, and I talked to you about his Psych project, right, that started in the 1980s and is still going on. Poor guy spent his entire life working on it, him and his team. Somehow the government's always given him enough funding to keep it going at some level. hoping it'll eventually strike gold. But you can see, because you go, well, all I really need to do is scale this thing up. If I could scale this thing up, it would be able to reason about the whole world, right? And I need to give these logical systems common sense. I need to come up with logical rules that fill in all the things that people never tell you. Like, once Lincoln died, he stayed dead, right? Unless you're reading something or watching a movie about, like Lincoln the Vampire or something. But the point is that if some people over the years thought one of the really common views of AI back in the 1980s and 90s was, well, if we could just logically encode enough common sense into computer programs, it'd be a huge, large database. But if we could do that, then we could use automated reasoning techniques to have an intelligent system. It hasn't worked out that way, right? I really liked Abraham Lincoln Vampire Hunter. I really actually liked that movie. What was I saying? But yeah, so people were excited about this. It's not come to pass yet. It probably won't come to pass, but maybe it will. Maybe in the end we'll end up with systems that, use neural networks and machine learning on some levels, and then on other levels use, logical rules to reason about things. It could happen. So what are we going to do from here? Well, next time we are going to introduce a technique called resolution refutation proofs. And resolution is you have to get your expressions into a standard form called conjunctive normal form. But if you can get all of your rules into conjunctive normal form, then you can basically go through canceling. It's a very simple algorithm that matches and cancels. And by doing that, you can build a theorem prover that'll take in some input and tell you if there's a contradiction. And that's really going to be kind of cool. So we'll do that next time. And when we finish that, we'll move on into predicate logic. Predicate logic lets you say things that are a little bit more general. For example, you can talk about, here's an example. All men are mortal. Remember I said after Lincoln died, he stayed dead? Well, all men are mortal, or more PC, all people are mortal, right? Men and women. You're basically expressing a rule about an entire class and saying, so if I said something like Marcus is a man, and I said that all men are mortal, then you can conclude that Marcus, since he's an instance of man and all men are mortal, you could conclude that Marcus himself is also mortal. So that's cool. And in prepositional logic as opposed to propositional logic, you can say things like, some people like science fiction. So you can make statements about individuals or subgroups, and you can make statements about entire groups in predicate logic, in predicate logic. And we'll get to that. We'll get to that next time. Okay? Are there any questions? Reminds you of logic puzzles. Yes, I agree with that. I think we went through everything there. Okay, well, I'm going to call it quits here for today. I will stay online to answer any questions after I stop the recording if anyone wants to do that. But for everybody else, I'll see you on Tuesday when hopefully we'll know who the President of the United States will be in January. Okay, talk to you guys later. Bye-bye.